Okay, we are back with more trigonometry coming at you. I could not be more excited to be on page 7 of the Trig Packet, right in the middle where we had left off. All over this page, you saw examples of finding trig functions of quadrantal angles. And we were constantly using this little unit circle sketch to help us because in the unit circle, conveniently, r is just 1. You can think of the x-coordinate as being your cosine value at that angle, the y-coordinate as being your sine value, and you can divide and use reciprocals to get the other trig functions. But we got to talk some notation in the middle here. There is a trig notation that's going to come up a lot and then in the next few math courses that you encounter that gets a little bit tricky, if you will, tricky, because of where they place the exponent when they mean to square a trig function. So what we have to start getting used to is if you see an example like this where it says cotangent of 90 degrees with the little squared on the inside instead of the outside, these are equivalent. What they mean to say is that you're finding the cotangent of 90, right, which I think is 0, and you're squaring that value. So here it says it equals 0 squared, which equals 0. But this is the way you'll more often see it printed in textbooks and on examples. So if you can square a trig function value, it shouldn't be too bad to figure these out. Try the first one. What this means to say is you're taking the sine of 90, even though the squared appears on the inside, you're squaring that whole expression. You're squaring that value. And then we'll add the cotangent of 90 and so on. So plus cotangent of 90, nothing really to rewrite there. You might want to rewrite this third part and find a smaller coterminal angle to 360 by subtracting, or to 630, by subtracting 360 from 630. We'll get sine of 270 instead. And now I think we can go to work. What's the sine of 90? What's the y coordinate up at 90 degrees? You're at that value 0, 1, right? The sine is going to be 1. So 1, turns out squaring it in this example doesn't really change anything. Plus, we were just talking about the cotangent of 90. So you're still at 90. Cotangent is that 0 over 1. X over r, or y, is going to be 0. Minus 4 times the sine of 270. So if you'll recall, 270 has coordinates 0, -1 on the unit circle, and -1 is going to be your sine. So I think now we just add and subtract, right? 1 squared plus 0 minus -4, that's going to be a plus 4 to get a 5 exact value. I really like the questions at the bottom here. I'm going to star this. You have to actually think the other way around, and we're going to try these just with our knowledge of the unit circle. It says find any angle or angles, some of these have more than one answer, on the interval from 0 to 360. We haven't used this interval notation too much lately in class this year, but it's easy to figure out. A hard bracket is inclusive, if you'll ever recall, and a soft parenthesis is not inclusive. So what this means to say is that theta is falling. If I just use inequality symbols, theta is going to fall between 0 degrees and 360 degrees for sure. But because the bracket goes with the 0, 0 is included on the interval, and because you're including 0 and 360 is the same as 0, it's the exact same angle in the same spot, you can just make this a soft inequality and not inclusive of the 360. So here's our boundaries. Where would the cosine of theta be -1? If I'm seeing trig function values, I'm getting 1s, -1s, 0s, undefineds. I'm thinking quadrantal. Where on this unit circle, at what quadrantal angle or angles, would the x value be -1? Cosine equals x. So think about it. Go on the x-axis, go to -1. -1 comma 0 happens at 180 degrees. Here, you're actually finding what's going to be called an inverse trig function. We're going to talk about this more in a second. But if theta were equal to 180, you would have a true statement. Make sure you put the degree sign on that answer. Because the cosine, you can check it. The cosine of 180 is -1. And that's a good solution on this interval. What about the next one, 15? The tangent of theta is undefined. Okay, so that means that happens a couple times using quadrantal angles. You're going to have something over 0. So we need to figure out tangent is y over x. We need to find the times quadrantally, I guess, where x would be 0, because then this would be true. You'd be dividing by 0. So where's x 0? Well, it's 0 up at 90 degrees, right? These coordinates are 0, 1. So the x is 0. And it happens again at 270 degrees. You're at 0, -1. So two different answers for this. I think if you plugged in theta equals 90, you'd have an undefined tangent. And then also, just continuing and still on this interval, 270 would also satisfy satisfy the equation. Okay, I want to see some more. Where would the cosine be 0? Where would the x be 0? Man, we're all about x here. So x is 0. I guess we kind of just answered that question, right? The 2 times where the tangent's undefined. So I'm going to put the same 2 answers for 16 as we did for 15, 90 degrees and 270 degrees. Just another way of asking you the same thing. Lastly, is there any quadrantal angle that would work for number 17? Where is the cosecant going to be -1? If I see some reciprocal trig function that's not one of my classics, sine, cosine, or tangent, I'm actually going to rewrite the equation first, for starters, and this is a good strategy, so that it is in terms of sine, cosine, and or tangent. If the cosecant equals this number, -1, what's the sine going to equal? What's its reciprocal going to be? Well, the reciprocal of -1, 1 over -1, happens to still be -1. So solving number 17, cosecant of theta equals -1, is the same as actually solving this equation. Where is the sine equal to -1? And I think it only happens once, right? The only time the y coordinate is going to be way down as low as it can possibly be on the unit circle, and -1 is going to be at theta equals 270 degrees. So just thinking about it the other way around. And I'm wondering, speaking of thinking, I'm wondering if you're thinking, man, these last couple lessons, this is a lot to do by hand. We haven't reached to my good friend the calculator yet. And you may have noticed that you have these nice sine, cosine, and tangent buttons right on the calculator. Why have we been neglecting them? It's better that we practice our skills by hand first, because you never know when you might be calculatorless, and that's going to happen a lot. You're going to need to know exact values of these trig functions, but let's just dabble a little bit. If you don't mind, could you flip 2 pages ahead? So I want to skip over to a page, it's 9 in my packet, where there's a heading at the top that says Trig on the calculator, and there's these 7 examples. They should be okay if we know the right mode and the right buttons to type in, but grab your calculator too to help. And we're starting with an example that says, and these all 3 say, can you approximate the value of the trig function using the calculator, the sine of 49.5 degrees? Well, when I go to my calculator, I mentioned something about your mode, and so far we've only been talking in degrees. I just want to make sure, I don't know who's been using this calculator last, and it looks like, do you see that radians happens to be highlighted on my screen? It's very important that I switch over. I'll hit enter for degree mode before I type in any trigonometric function. So we need to be in degree mode. I'll even put that at the top. That's really important. Degree mode. And we will use radians. That's a sneak preview on another day, but not today. So then I want to type in, where do you see sine? So I see a sine, cosine, and tangent button in the middle of the screen. So I want the sine of 49.5, 49.5 degrees. Don't really need to end the parentheses, but I'll do it anyway. And we get 0.760 when it gets rounded. That's what the calculator tells me. So I'm going to write that down and see if we can interpret that. 0.760. Does this seem like an okay solution? Now think about when we were finding sine, cosine, and tangent. What quadrant does 49.5 lie in? So it's in quadrant 1, right? Right around there. If you were to make a right triangle, here's your theta. What we just figured out here is that the ratio, sine is the ratio from, you might have remembered it from SOHCAHTOA, your opposite side to your hypotenuse, or your y over r. And we just figured out that y over r equals 0.76. Good that it's positive, because you're in quadrant 1, it should be positive there. And also, good that it's not too high of a value. Do we know the highest that sine could ever get to? Sine is at its highest when you get to 90 degrees. The highest sine could ever be is going to be the number 1, because it's a ratio. How could the y ever be bigger than the r? In those 3, the x, y, and the r has got to be at or the biggest of the 3 values. So I like an answer like a 0.76. Wait till you see this one. Okay, so 2 is a good one to star. The secant of 89.97, almost a right angle. Unfortunately, if I look at the calculator, I'm missing 3 trig functions here. I don't see a secant, a cosecant, or a cotangent. We're not going to use these yet, the sine with the -1, cosine with the -1. Can you hold off on those? Instead, let's think about it. If I could get the cosine of 89.977 and flip it, I would have the secant. So instead of typing in secant, because I don't have that button, I'll go 1 divided by the cosine of 89.977. 0.977 degrees. I'm going to have a pretty big value for this one. Hit enter, and I'll talk about why it's so big. So up in the 2000s, between 2000 and 3000, here's how I type it into the calculator. With no secant key, I'll go 1 over the cosine of 89.977. And rounded to the nearest thousandth, it's going to be 2,491.121. How am I allowed to get such a huge value for secant when I'm restricted for sine between -1 and 1? Well, think about it. If sine and cosine have to fall within -1 and 1, their reciprocals must be outside of that range. And really, it's hard to draw this angle. It would be such a tall right triangle because your angle is almost 90 degrees that you have such a huge y side, right? And a very, very tiny x side, so small that when you do 1 over a tiny, tiny value, you're going to get a huge number like that. Can you try 3 the same way? What trig function should you use? If you don't have a cotangent key, what's a good reciprocal to use? Let's go with 1 over tangent of that whole decimal, 51.4283 degrees. Go ahead, type that in, 1 over the tangent. I can wait, you can pause. I want you to check my answer of a 0.797. See if that looks good. Straight from the calculator. All right, underneath, we've seen a question or two like this a couple pages ago, and we're doing the opposite. We're using a calculator not to find the sine, cosine, or tangent, to find out what angle would make this equation true. So to find out an angle where the sine would be roughly this decimal. Well, using a calculator, I wish to solve this equation, I could do something silly, and I'm about to erase this. Do not write this. I wish I could just divide by SIN and SIN to get the theta by itself and call it a day. Well, that doesn't make any sense. We've talked in the past before about how sine without the theta after it doesn't have any mathematical meaning. So one thing I cannot do to get theta by itself is just divide by sine. What you're going to do with a calculator is you're actually going to take the inverse sine of both sides. So the sine to the -1 of this side and sine to the -1 of the other side. It's an annoying part of mathematics when one notation could mean 2 different things. So I know that -1 power reminds me of x to the -1 means to flip. But here, this is actually not what we're using this time. The inverse sine, or sometimes it's called the arc sine. In pre-calc and calc, you'll sometimes call it the arc sine or the arc cosine, meaning the arc or angle, right? These two cancel with each other. All you're left with is theta, and your calculator is going to give you the theta value where this would be your sine. The 0.9677 would be your sine. So you want to take the inverse sine of 0.9677. We'll put that into the calculator. So second, and the sine key, 0.9677. And you get an angle measure. Let's put degrees on it. Let's just do nearest tenth here. We'll say about 75.4 degrees. You can check this answer. If you type in now sine of 75.4, now I know this is rounded, so it won't be exact, but you'll get something that's close to 0.9677. Let's try the next one. Ooh, this is a good one. So for 5, this is a reciprocal trig function. Before you do anything on the calculator, I want you to rewrite it. We don't have a secant button, so let's write what the cosine would be. The cosine of theta would equal 1 over 1.0546. That's for sure. So to get theta by itself, you're looking for an angle. So that means I know I need to use the second and cosine key, the inverse cosine of 1 over 1.0546. Let's go back to the calculator. So inverse cosine first before you do the 1 over, second and cosine. 1 over, what was the number? 1.0546. Hit enter, and you get the angle, 18.5 degrees when rounded. Okay, so that was important. What about cotangent equaling 5? Flip it first. It's a reciprocal. Change it right now immediately into tangent, and that's going to be 1 over that original value. You're going to take the arc tangent, or the inverse tangent of 1/5 to get this answer. We'll type it in and round it. So second tangent, 1/5. And you get an angle. I'll round this to 11.3 degrees. Okay, last one. When I try the inverse cosine, the arc cosine of 3, let's see what the calculator gives me. So I go inverse, second, and cosine of 3. And I'm afraid I did something wrong because it says arrow domain. Go to is sometimes what I hit. It brings me back to this. This is undefined. We'll talk much more later about how the cosine could never be 3 because the highest it could ever be is 1. So sometimes you get an error. Hope you enjoyed. Cannot wait to talk to you again. See you soon.